Chapter 4, Standardization and Z-Scores. If you know the mean and standard deviation of a distribution of scores, you have enough information to develop a picture of the distribution. Sometimes researchers are interested in describing individual scores within a distribution. Using the mean and the standard deviation, researchers are able to generate a standard score, also called the Z-score, to help them understand where an individual score falls in relation to other scores in the distribution. Through a process of standardization, researchers are also better able to compare individual scores in the distributions of two separate variables. Standardization is simply a process of converting each score in a distribution to a Z-score. A Z-score is a number that indicates how far above or below the mean a given score in the distribution is in standard deviation units. So standardization is simply the process of converting individual raw scores in the distribution into standard deviation units. Suppose that you are a college student taking final exams. In your biology class, you take your final exam and get a score of 65 out of a possible 100. In your statistics final, you get a score of 42 out of 200. On which exam did you get a better score? The answer to this question may be more complicated than it appears. First, we must determine what we mean by better. If better means percentage of correct answers on the exam, clearly you did better on the biology exam. But if your statistics exam was much more difficult than your biology exam, is it fair to judge your performance solely on the basis of percentage of correct responses? A more fair alternative may be to see how well you did compared to other students in your classes. To make such a comparison, we need to know the mean and standard deviation of each distribution. With these statistics, we can generate Z-scores. Suppose the mean on the biology exam was 60 with a standard deviation of 10. That means you scored 5 points above the mean, which is half of a standard deviation above the mean, so higher than the average for the class. Suppose further that the average on the statistics test was 37 with a standard deviation of 5. Again, you scored 5 points above the mean, but this represents a full standard deviation over the average. Using these statistics, on which test would you say you performed better? The stats test. To fully understand the answer to this question, let's examine standardization and Z-scores in more depth. Standardization and Z-scores in depth. As you can see in the previous example, it is often difficult to compare two scores on two variables when the variables were measured using different scales. The biology test was measured on a scale from 1 to 100, whereas the statistics exam used a scale from 1 to 200. When variables have such different scales of measurement, it is almost meaningless to compare the raw scores, i.e. 65 and 42, on these exams. Instead, we need some way to put these two exams on the same scale or to standardize them. One of the most common methods of standardization used in statistics is to convert raw scores into standard deviation units, or Z-scores. The formula for doing this is very simple and is presented in Table 4.1. As you can see from the formulas in Table 4.1, to standardize a score, i.e. to create a Z-score, you simply subtract the mean from an individual raw score and divide this by the standard deviation. So if the raw score is above the mean, the Z-score will be positive, whereas a raw score that is less than the mean will produce a negative Z-score. When an entire distribution of scores is standardized, the average, i.e. mean, Z-score for the standard distribution will always be 0, and the standard deviation of this distribution will always be 1.0. Table 4.1, formula for calculating a Z-score. Z equals raw score minus mean, all divided by the standard deviation, or Z equals big X minus mu, all divided by theta, if you're looking at a population, or Z equals big X minus X bar, all divided by S, where you're looking at a sample, where big X is the raw score, mu is the population mean, theta is the population standard deviation, X bar is the sample mean, and little s is the sample standard deviation. Interpreting Z-scores. Z-scores tell researchers instantly how large or small an individual score is relative to other scores in the distribution. For example, if I know that one of my students got a Z-score of negative 1.5 on an exam, I would know that student scored 1.5 standard deviations below the mean on that exam. If another student had a Z-score of 0.29, I would know that student scored 0.29 standard deviation units above the mean on the exam. Let's pause here and think for a moment about what Z-scores do not tell us. If I told you that I had a Z-score of 1.0 on my last spelling test, what would you think of my performance? What you would know for sure is that A, I did better than the average person taking the test, B, my score was one standard deviation above the mean, and C, if the scores in the distribution were normally distributed, my score was better than about 2/3 of the scores in the distribution. But what you would not know would be A, how many words I spelled correctly, B, if I am a good speller, C, how difficult the test was, D, if other people taking the test are good spellers, E, how many other people took the test, and so on. As you can see, a Z-score alone does not provide as much information as we might want. To further demonstrate this point, suppose that after I told you I had a Z-score of 1.0 on the spelling test, I went on to tell you that the average score on the test was 12 out of 50 and that everyone else who took the test was 7 years old. Not very impressive in that context, is it? Now, with the appropriate cautions in mind, let's consider a couple more uses of Z-scores in standardization. One of the most handy features of Z-scores is that, when used with a normally distributed set of scores, they can be used to determine percentile scores. That is, if you have a normal distribution of scores, you can use Z-scores to discover which score marks the 90th percentile of a distribution, i.e., that raw score at which 10% of the distribution scored above and 90% scored below. This is because statisticians have demonstrated that in a normal distribution, a precise percentage of scores will fall between the mean and one standard deviation above the mean. Because normal distributions are perfectly symmetrical, we know that the exact same percentage of scores that falls between the mean and one standard deviation above the mean will also fall between the mean and one standard deviation below the mean. In fact, statisticians have determined the precise percentage of scores that will fall between the mean and any Z-score, i.e., number of standard deviation units above or below the mean. A table of these values is provided in Appendix A. When you also consider that in a normal distribution, the mean always marks the exact center of the distribution, you know that the mean is the spot in the distribution in which 50% of the cases fall below and 50% fall above. With this in mind, it is easy to find the score in a distribution that marks the 90th percentile, or any percentile for that matter. In Figure 4.1, we can see the percentage of scores in a normal distribution that fall between different Z-score values. This figure contains the standard normal distribution. Figure 4.1, the standard normal distribution. So you can see in the middle, at the peak of the normal curve, mu equals 0, which is the mean is 0, and then you can see a line dividing the normal curve into 1 theta, 2 theta, and 3 theta, showing up to 3 standard deviations away from the mean at -1 theta, -2 theta, and -3 theta, dividing up the whole bell curve. And then under that, you can see the Z-scores that correspond to the standard deviation. So when it's divided into 1 theta, the Z-score is 1. When it's divided at 2 theta, the Z-score is 2. When it's divided at 3 theta, the Z-score is 3. When it's divided at -1 theta, the Z-score is -1. When the normal curve is divided at -2 theta, the Z-score is -2. And when the normal curve is divided at -3 theta, the Z-score is -3. Let us consider an example. Suppose I know that the average SAT math score for white males is 517 with a standard deviation of 100 and forms a normal distribution. In this distribution, I already know that the score that marks the 50th percentile is 517. Suppose I wanted to know the score that marks the 90th percentile. To find this number, I have to follow a series of simple steps. Step 1. Using a Z-score table from a traditional statistics textbook, find the Z-score that marks the 90th percentile. To do this, we need to remember that the 90th percentile is 40 percentile points above the mean. So we are looking for the Z-score at which 40% of the distribution falls between the mean and this Z-score. An alternative method is to find the Z-score at which 10% of the distribution falls above, because the 90th percentile score divides the distribution into sections with 90% of the score falling below this point and 10% falling above. Z-score tables in traditional statistics textbooks always provide at least one of these scores, i.e. the percentage of the distribution that falls between the mean and the z-score, or the percentage that falls above the z-score, and often both. In the current example, the z-score that corresponds with the 90th percentile is 1.28, so z equals 1.28. Step 2. Convert the z-score back into the original unit of measurement. Remember that the SAT math test is measured on a scale from 0 to 800. We now know that the mean for white males who took the test in 1989 was 517, and that 90th percentile score of this distribution is 1.28 standard deviations above the mean, because z equals 1.28. So what is the actual SAT math score that marks the 90th percentile? To answer this, we have to convert our z-score from standard deviation units into raw score units and add this to the mean. The formula for doing this is big X equals mu plus z times theta. In this equation, X is the raw score we are trying to discover, mu is the average score in the distribution, z is the z-score we found, and theta is the standard deviation for the distribution. Plugging our numbers into the formula, we find that big X equals 517 plus 1.28 times 100. Big X equals 517 plus 128. Big X equals 645. Now we can wrap words around our result and answer our original question. When doing this, it is often helpful to use the original question when stating our finding as follows. Question: what is the score that marks the 90th percentile of the distribution of white males' SAT math scores in 1989? Answer: the score of 645 marks the 90th percentile of the distribution of white male students' SAT math scores in 1989. This z-score, percentile score, and the corresponding raw score are depicted in figure 4.2. So the formula to find the raw score, big X equals mu plus z times theta, is a rearrangement of the formula to find the z-score, which is z equals big X minus mu divided by theta. So you only need one formula technically to be able to find both the z-score, if that's what you need, or to find the x-score, if that's what you need. Figure 4.2, finding the score that marks the 90th percentile of the distribution. Okay, so you can see in the middle of the normal curve, x equals 517, the mean, z equals 0 is the 50th percentile. And then you can see above that on the right-hand tail, you can see x equals 645, z equals 1.28, and it's the 90th percentile. Just as we can use z-scores to find the raw scores that marks a certain percentile in a distribution, we can also use z-scores to help us convert a known raw score into a percentile score. For example, if I know that a student in my distribution has a score of 425 on the SAT math test, I might want to know the percentage of the distribution that scored above and below 425. This is the type of conversion that has happened when students' standardized test scores are published in the local newspaper using percentiles under headlines such as California students score in 45th percentile on national test. Similarly, when a proud parent exclaims, "My Johnny is in the top 10% in height for his age group," a conversion from a raw score to a percentile score has taken place with the help of a z-score. Here's how it's done. Step 1. We must begin by converting the raw score into a z-score. In our example, the raw score is 425. X equals 425. To convert this to a z-score, we simply recall that our mean, mu equals 517, and our standard deviation, theta equals 100, and then plug these numbers into the z-score formula. Z equals big X minus mu divided by theta. Z equals 425 minus 517, all divided by 100. Z equals negative 88 divided by 100. Z equals negative 0.88. Step 2. Now that we have a z-score, we need to look at the nearest z-score table to find either the percentage of the normal distribution that falls between the mean and a z-score of negative 0.88, or the percentage of the distribution that falls below a z-score of negative 0.88. Notice that we are dealing with a negative z-score in our example. Most Z-score tables only report positive Z-scores, but because normal distributions are symmetrical, the percentage of the distribution that fall between the mean and Z are identical whether the Z-score is positive or negative. Similarly, the percentage that falls above a positive Z-score is identical to the percentage that falls below a negative Z-score. My Z-score table tells me that 31% of the normal distribution of scores will fall between the mean and a Z-score of negative 0.88, and 19% will fall below a Z-score of negative 0.88. Step 3. To wrap words around this result, I must begin with the recollection that in my example, a Z-score of negative 0.88 corresponds to a raw score of 425 on the SAT math test among the white males who took the test in 1989. So to wrap words around my result, I would say that a score of 425 on the SAT math test marks the 19th percentile of the distribution of test scores among white males in 1989. The examples just presented represent two handy uses of Z-scores for understanding both an entire distribution of scores and individual scores within that distribution. Standardized scores are used in a variety of statistics and are perhaps most helpful for comparing scores that are measured using different scales of measurement. As discussed earlier in this chapter, it is difficult to compare two scores that are measured on different scales, for example height and weight, without first converting them into a common unit of measurement. Standardizing scores is simply this process of conversion. In the final section of this chapter, I present and briefly describe two distributions of scores described by both raw scores and Z-scores. Examples: comparing raw scores and Z-scores. To illustrate the overlap between raw scores and standardized Z-scores, I first present data from a sample of elementary and middle school students from whom I collected data a few years ago. I gave these students a survey to assess their motivational beliefs and attitudes about a standardized achievement test they were to take the following week. One of the items in the survey read, "The ITBS test will measure how smart I am." Students responded to this question using an 8-point scale with 1 strongly disagree and 8 strongly agree. The frequency distribution is presented in figure 4.3. This distribution has a mean of 5.38 and a standard deviation of 2.35. As you can see, this is not a normal bell-shaped distribution. This distribution has a sort of odd shape where there is the hint of a normal distribution in scores 2 through 7, but then there's spikes at the ends, particularly at the high end. The result is an asymmetrical distribution. If you compare the Z-scores on top of each column with the raw scores at the bottom of each column, you can see how these scores are related to each other. For example, we can see that all of the raw scores of 5 or lower have negative Z-scores. This is because the mean of a distribution always has a Z-score of 0, and any raw scores below the mean will have negative Z-scores. In this distribution, the mean is 5.38, so all raw scores of 5 and below have negative Z-scores, and all raw scores of 6 or above have positive Z-scores. Another feature of this distribution that is clearly illustrated by the Z-scores is that there is a larger range of scores below the mean than there are above the mean. This is fairly obvious because the mean is well above the midpoint on this scale. The highest scores in this distribution are just a little more than 1 standard deviation above the mean. Z equals 1.12, whereas the lowest scores are nearly 2 standard deviations below the mean. Z equals negative 1.86. Finally, the inclusion of standard deviation scores with each raw score allows us to immediately determine how many standard deviations away from the mean a particular raw score falls. For example, we can see that a student who had a raw score of 3 on this variable scored just about exactly 1 standard deviation below the mean. Z equals negative 1.01. Figure 4.3, frequency distribution for "the test will show how smart I am" item. Okay, so you can see that, the mean on this graph is this bar graph is between 5 and 6, score on the raw score, because a 5 corresponds to a Z-score of negative 0.16, and a raw score of 6 corresponds to a positive Z-score of 0.27, so the mean is in the middle there. Yeah, and you can see the distribution is skewed to the left because the range is higher of the values on the left side from the mean. It goes out, like they said, to almost -2 standard deviations, whereas the upper range only goes to about 1 standard deviation. So you can see too that the x-axis is of course the raw scores, and the y-axis is the frequency of each raw score in the bar graph. For our second example, I have chosen a variable with a much smaller standard deviation. Using the same 8-point scale described earlier, students were asked to respond to the item, "I think it is important to do well on the ITBS test." Students overwhelmingly agreed with the statement, as the mean 7.28 and relatively small standard deviation 1.33 revealed. The frequency distribution for the scores on this item is presented in Figure 4.4. Figure 4.4, frequency distribution for important to do well item. Yeah, so you can see the mean falls between 7 and the raw score of 7 and 8, because a raw score of 7 corresponds to a z-score of -2.1, and for a score of 8 corresponds to a z-score of positive 0.54. You can also see the distribution is very skewed to the left. Most of the points are to the left. And yeah, so the standard deviations, they do go down all the way to a z-score of -4.72. So that is actually a large spread. And the frequency of the raw scores is on the y-axis in numbers. In this graph, we can see that the distribution is highly skewed, with most students circling the number 8 on the scale. Because so many students answered similarly, the standard deviation is quite small, with only a relatively few scores at the lower end of the distribution. This small standard deviation, coupled with the high mean, create a situation where very low scores on the scale have extremely small z-scores. For example, the few students with a raw score of 1 on the scale, n equals 7, had z-scores of -4.72, indicating that these students were more than 4 standard deviations below the mean. Those students with the highest score on the scale were only about half a standard deviation above the mean, because, with such a high mean, it was impossible to get a score very far above the mean. The two examples provided previously both illustrate the relation between z-scores and raw scores for distributions that are skewed. In both of these distributions, the means were above the midpoint on the scale, and subsequently there was a greater range of z-scores below the mean than there were above the mean. Such is not the case when the distribution of scores are normally distributed. To illustrate this, I use data from a different data set. I use surveys to measure a sample of high school students' motivational goals in school. One goal that I measured is known as a performance approach goal. This goal reflects a concern or a desire to outperform classmates and peers for the sake of demonstrating superior ability. The items on the survey were measured using a scale from 1 to 5. 1 equals not true at all, and 5 equals very true. The frequency distribution is presented in Figure 4.5. This distribution of scores has a mean of 3.0 and a standard deviation of 0.92. As you can see, the data are quite normally distributed. When the data are normally distributed, we would expect most of our cases to have z-scores at or near 0, because in a normal distribution, most of the cases are near the mean. Also notice that as we move farther away from the mean, i.e. z-scores of over 2.0 or less than -2.0, there are fewer cases. In a normal distribution, then, the probability of finding a particular z-score becomes smaller as the value of the z-score moves further away from 0. As figures 4.3 and 4.4 illustrate, this is not always the case in skewed distributions. So in the standard normal curve, in the middle of the bell curve, at the peak of it, mu, the mean, is 0, the standard deviation, theta, is also 0, and the z-score is also 0, corresponding to the standard deviation of 0. Figure 4.5, frequency distribution for performance approach goals. Okay, so you can see that for the raw score of 3, z equals 0, which means that is the mean. The mean raw score is 3. Okay, you can also see that it's symmetrical. So the bar to the right of 3, which the score of 4, has a z-score of 1.08, and the bar to the left of the mean has a z-score of negative 1.08, so they're matching numbers. And then out one more bar for a score of 5, the z-score is 2.15, and then all the way to the left for a z-score of 1, the z-score is negative 0.25, so it's matching numbers with a negative sign. And on the y-axis is the frequency in numbers. Wrapping up and looking forward, z-scores provide a handy way of interpreting where a raw score is in relation to the mean. They also demonstrate that the range of possible z-scores depends heavily on where the mean falls in the range of possible scores, as well as the size of the standard deviation for the distribution. We can use z-scores to quickly and easily determine where an individual score in a distribution falls relative to other scores in the distribution, either by interpreting the z-score in standard deviation units or by calculating percentile scores. Using the table of probabilities based on the normal distribution presented in Appendix A, we can also use z-score to determine how unusual a given score in a distribution is, i.e., the probability of obtaining an individual score of that size when selecting the individual at random. In the next chapter, we will use the information that we have learned about the mean, standard deviation, normal distributions, z-scores, and probability to understand one of the most important concepts in statistics, the standard error. Glossary of terms and symbols for Chapter 4. Raw scores. These are the individual observed scores on measured variables. Standard score. A raw score that has been converted to a z-score by subtracting it from the mean and dividing by the standard deviation of the distribution. It is an individual score expressed as a deviation from the mean in standard deviation units. Standardization. The process of converting a raw score into a standard score. Z-score. Another term for a standard score. Z. The symbol for a standard score. Big X. The symbol for a raw score. Mu. The symbol for a population mean. Theta. The symbol for a population standard deviation.